you're basically saying that if you're accelerating in a car, that gas molecule hits the back of the car, then starts accelerating forward to the front of the car.
Yo, Flurs, I hope you're all doing well. Thank you for coming. Today's going to be an interesting one because recently QE had Rachie on to explain her relative density disequilibrium invalidation and why she thinks it's an accelerating up Earth. Well, I don't want to strawman Rachie, so I thought I'd rather make a video letting her give her arguments and then let me give rebuttals to the argument to show why it's incorrect. Stay tuned. Enjoy.
Yes, my question is a very simple one. I want to know what the claim is, whether it started with you or Dell. What is just succinctly?
For the upwards moving Earth, right?
Is that the claim? Is the Earth rising up?
See, me and Dell claim something a bit different. I don't really make a claim, it's more of a thought, but possibility, shall we say. But okay. Dell claims different to me. He claims a constant speed, whereas I claim possibly an accelerating. But I'm not saying it's definite, just more of a maybe.
So there we have it. Rachie claiming an accelerating upwards Earth, while Dell is claiming a constant velocity upwards Earth. They both have the issues though. Do you think they're going to be able to demonstrate this to be the truth? Or is it just going to be a conjecture based on, well, belief?
Well, it's possible.
Okay.
Yeah.
Okay. Oh, go ahead. Go.
Wow.
Nope. Go ahead, Adam.
Okay. So that in of itself is quite interesting. As I said, if people present things as pure conjecture, they not using their conjecture to attack established things for some strange reason. I'm not accusing you of that, but there are Umis and Etherians that do that same thing. Why are you supporting this conjecture? What purpose? Yeah, like there's all sorts of conjecture I'd make, but for me to get behind it, there has to be a reason. I'd ask you, what's your motivation is in following this particular line of conjecture?
So for me, the reason I joined FE or found FE to begin with was because basically I found out about gravity and it was not a force and it was bendy space-time, and obviously we all know how ridiculous that is. So then I thought, well, why do things fall and go up? And then obviously I come to relative density disequilibrium and found Eric Debye and then found flat Earth. So this is like another inquiry into if it's not relative density disequilibrium because of obviously Dell's explanation, which I was arguing against to begin with, and dropping a bottle and then not seeing less dense and more dense fall relative to the medium and rise relative to the medium based on their densities, then maybe there's another reason why that happens. And then basically that's where I am at now.
First we'll start off with drawing the Earth. Let's just make a grass bank for argument's sake. We will now draw a container. This container is just held by someone in their hand. This means the container would be static. It's not moving anywhere. It has no magnitude. It's staying where it is. We do know that now we have gas inside this container, bouncing all around, all over, non-stop. As we know, gas has elastic collisions. They move around in all directions constantly. So now let's add a denser substance inside the static container. Let's add some water. We had our water, and what do you know? The water is denser than the air around it. So remember, the water and the air are all in the same container. They're in the static position. So the water has a greater impulse than what the gas would have. Because what is impulse? That's just the explaining of the impulse. It explaining impulses is reference to a weak force acting over a period of time. So if you explain how an impulse works, if you think of a quick shudder, let's say someone, if you just have a quick bang, that would be an impulse. You had an impulse of force. So that is how the impulse works. And then obviously note that the F is referring to general function of time. This constitutes that it is a force with varying time. What this is telling us is that the change in the momentum of the system doesn't depend on the detailed time dependence of F, but rather the integral of F. So in other words, the variation of F. So it's the variation of the force applied due to time. So what is impulse? I'm trying to explain it as simple as possible. Impulse is simply the product of the force being applied times the time over which the force is being applied. Let's take an example of two balls falling to the ground. We're going to imagine them falling at the same velocity and have the same mass. Okay? See, the one is bouncing and the other one just hit straight and stopped. What did we see there? Wow. The time of interaction was less with the ball on the left and the time of interaction was more on the right. That is, so had a different impulse. Okay, what do we see? We saw the ball on the left side had shorter interaction period compared to the right side ball. This means that the ball on the right is applying less force to the table and compared to the ball on the left. So we saw as soon as it just had a hit, it just put on more force applied to the table, and the one that was bouncing had less force because of the impulse. So momentum will change over time. Impulse is a force applied over time. Now, how is this significant? Well, if we take the based on the presented demonstration, we can see the relationship between the object and the medium and the forces relative to what we observe. So we see at static, the gas and the water have separated due to their densities. Let's now add a object into the mix. We'll just add a little ball for argument's sake, but we'll say the ball is denser than the air and less dense than the water. So obviously we're going to see the air is separated, it's the least densest, and we have the ball coming in at a second with denser than the air and less dense than the water, and the water being denser than the object and the air. They're all in what? Static containment. So it's not moving. Now, they have to take another demonstration. What happens if you take this same container and make it not static anymore? That means it would be accelerating downwards. It would have momentum. It has a magnitude. And we go and we mix everything up in this container. So in other words, this little ball will now be floating around here, and we're going to have some water all over the place inside there, you know, going haywire. We got it all around here, and it's moving up, it's all there, and we're gonna have some air mixed inside the bottom here. Okay, that was now what we showed it to be. We shook it around just before we let it go. Now we have to understand that this is not static. Okay, not static. What will be the reaction? Why would you expect that this should go and show its relative denser ratio separations, just like we saw with the static demonstration? Why would you expect that? Remember, when you have the static demonstration, everything has a difference in the impulse it's having. So in other words, the magnitude of the force attributed is different. There's no movement. The one has more pressure than the other one applied. So if it's got more weight, it's applying more of a pressure. Now with the gas, if it's not in static motion, this object, the water, all the gas, and the container are all accelerating to the ground. So until they meet the ground, they all accelerate at the same rate. So they are having exactly the same amount of impulse attributed to them. They will not be going to change their ratios like in the static demonstration, because in the static demonstrations they all have a different ratio of force attributed to them, where when they're moving they all have the same rate of force. So they move at the same rate. The object, the water, and the air, and the container all accelerate down to the earth at the same accelerative rate. This means that they would not be able to separate and does not destroy relative density disequilibrium, because they still have the same densities. The difference is the accelerative forces due to it falling, falling F equals ma, because there's a force attributed to have the mass to accelerate. Remember, according to Newton's laws of motion, equal and opposite reaction.